Hello and welcome back to Measure Theory. And as always, first I want to thank all the nice supporters on Steady or PayPal. Now, in today's part 3 about outer measures, we will fill in some details of a proof from the first video. There, please recall, we've discussed an important proposition. The proposition tells us that each outer measure phi can be transformed into an ordinary measure. More concretely, we have two parts. The first part A tells us what the corresponding sigma algebra A phi is. In fact, it turns out when we consider all subsets A in X that are phi measurable, we get a sigma algebra. Of course, you know, this is the first ingredient we need for an ordinary measure. And exactly this one we call mu in part B. Now the domain of mu is given by our new sigma algebra, and the definition is given by the outer measure phi. In other words, mu of A is given by phi of A. And then the claim is, this is now a normal measure. Okay, there you see, this is a nice proposition we already introduced in part 1. Therefore, now in this part I want to give you the ideas for the proof. This means that for the first part we have to verify all the properties of a sigma algebra. These are essentially three things. First, the empty set and X should be in A phi. Then the collection of sets should be closed under the complement and closed under countable unions. Hence, I would suggest we start with the simplest one, checking if the empty set is in A phi. So by definition, this means is the empty set phi measurable. So I think this is a good point, refreshing your memory what phi measurable actually means. A subset A is called phi measurable if it fulfills the following relation. Namely, if A decomposes every other set Q into two parts such that we have this additivity for phi. Now in the case that A is the empty set, we see this relation immediately. Because the first part is just the empty set again, and the second part is just Q. Of course, you see these intersections are not hard at all. And then we just need the fact that an outer measure sends the empty set to 0. Hence, the whole first part is just 0 and the relation holds. And there you see, one property for the sigma algebra is already satisfied. Then the next question would be, can we do the same for the whole space X? So again, we have the question, is the whole space X phi measurable? And to answer that, we have to take the relation again for every set Q, but now we put in X. And there you see, this looks very similarly because the complement of the whole space is of course the empty set again. So you see, this is exactly the same as before, just the two terms in the sum have switched roles. Hence, we can also conclude X is phi measurable. Okay, with this let's go to the next property of a sigma algebra. Namely, the question is the whole collection of subsets closed under complements? Hence, we start with one subset A that is phi measurable. Then, in the end, of course, we want to conclude that the complement of A lies also in A phi. Indeed, how this proof works, you might have already seen above when we considered the empty set and the complement X. Of course, we need to do it in a similar way because we only have this relation to work with. Here, please always keep in mind, I don't write it down, this relation holds for every subset Q. Okay, then let's do what we have done above, let's exchange the two terms in the sum. In fact, this is almost what we want to have for the relation of AC. In the first part, we already have AC, and in the second part, we need the complement of AC. However, this is already given simply because the complement of the complement is the original set again. Okay, now here when you look at the left hand side and the right hand side, you see this is exactly the definition for AC being phi measurable. Hence we see the second part for the sigma algebra is also fulfilled. So only the hardest one remains to show. And here it's, as you can see, the property that the sigma algebra is closed under countable unions. And we know this is related to the sigma additivity of the corresponding measure mu. Therefore, both things in the proof will go hand in hand. However, before we do this, we first should show that our A phi is indeed closed under a finite union. Which means we have to consider two sets. So we choose A1 and A2 from our A phi, and then we show that the union of both sets lies also in A phi. As before, this simply means we have to show that this property here holds for every set Q. Therefore, we already know our goal here. So let's put this to the bottom then. Here, please also recall it's sufficient by the definition of an outer measure to show the one inequality here. Okay, then I would say let's start bringing the two properties for A1 and A2 together. First, let's apply it to A1. Then, in order to bring A2 in, let's call the second part here Q tilde. Hence there, we now can apply the property for A2, but now instead of Q, for Q tilde. Which means we don't change the first part, but then we have two more terms, which look like phi of Q tilde intersected with A2 plus the same with the complement. However, remember, in the end, we only want two terms. Hence, the overall idea now is that we put the first two terms here together. And in fact, we are allowed to do this using the sigma subadditivity of the outer measure phi. However, this now means we get an inequality in. This is simply the sub in subadditivity. And the rest of the property tells us that instead of the plus, we have a union inside of phi. Okay, here you can see our result. We have two terms for phi now. In the one, we find A1 and A2, and in the other one, we find the complement of both sets. So it seems like this is almost the thing we want. Indeed, the second part we immediately recognize as the correct one, simply because Q tilde was defined as Q intersected with A1 complement. In other words, we can write it like this. And then, when we pull out the complement, we find the union. Okay, very good. This is exactly the term we wanted. Now, looking at the first part, it looks more complicated. However, we can also transform it to this. And maybe we just verify this with a Venn diagram. This works because we have exactly three sets involved: Q, A1 and A2. Okay, then let's start with Q intersected A1. This intersection, you see, we simply find here. And now the other intersection is an intersection with three sets. First we have Q, then A1 complement, and then A2. And then it's not hard to see that this is exactly this small part here. Okay, and then you see, this Venn diagram explains exactly this intersection here. Hence, the proof of the union with two sets is indeed finished. The union A1 with A2 is also in A phi. Okay, then we can go to the next part where we have to consider countably many sets. Hence here we need a whole sequence of subsets A1, A2 and so on. They all should come from A phi, and then the question is the union from j is equal to 1 to infinity also an element in A phi? For this we want to find a positive answer. Hence, for the rest of the proof, it might be helpful to give this union a shorter name, so let's simply call it A. Now I can tell you, instead of taking an arbitrary sequence of sets here, we can take a pairwise disjoint one. This is possible because we have already proven the closeness with respect to the normal union and also the closeness with respect to the complement. Therefore we can simply do this, but it also has the big advantage that we immediately get the sigma additivity for the measure mu in the end. Because in order to show this, you know, we need to consider pairwise disjoint sets. Hence, in summary, it's indeed helpful to do the proof like this. Of course, here at the start of the proof, it might not surprise you that again, we use the property the outer measure gives us. However, here I want to put in a special set Q. First, we could have any set, so let's simply call it Q hat. And then we put in the intersection of A1 in the union with A2. And here, please keep in mind, A1 and A2 are disjoint. This fact will help us on the right hand side when we put in the same set for the set Q. For example, in the first part, you see the intersection with A1 here will completely cancel out A2. Therefore, the first part is just Q hat intersected with A1. Then in the second part, because we have the complement of A1, this will completely cancel out A1 itself. So we simply have phi of Q hat intersected with A2. Okay, so you should see this is a nice trick to get the union on the left hand side and a sum on the right hand side. Hence, the next step would be to do an induction to get finitely many sets in. So the induction shows we have phi of Q hat intersected with a finite union. So you see, this whole thing here is simply the left hand side. And then the right hand side is given by a sum. Of course, also from j is equal to 1 to n. And inside we have phi of Q hat intersected with aj. Okay, so this is a nice result, which holds for every n, so we should give it a name, let's call it star. Now let's go one step back and recall what we already know. Namely, we know that this union here is by our proof above also an element in A phi. So we don't have the infinite union yet in A phi, but we are getting closer. Because when we know that this is an A phi, we can use the property as always, the property for the outer measure. So this works as before, but now instead of Q we use Q hat, and instead of our A we have here the union of the AJs. Now for the first part you should see we can use our star property to rewrite that as a sum. So you see, with each step we are getting closer and closer to the sigma additivity. Okay, then for the second part here, we use something we didn't use before, but where we know it holds for an outer measure. Indeed, it's the second property an outer measure has, the monotonicity. We can use that here because when we increase the index n here, this whole set here would get smaller. Therefore, we can also do it for n to infinity. Then we have the infinite union, which we simply called A. So the second part is greater or equal than phi of Q hat intersected with AC. Okay, with this we now have something where there is no index n in a union anymore. Indeed, we have here an inequality that holds for all natural numbers n. Therefore, this inequality also holds the limit n to infinity. Hence, phi of Q hat is greater or equal than the infinite sum of phi of Q hat intersected with aj, plus the second term phi of Q hat intersected with AC. So here you see we have an infinite sum, and remember we want to show the sigma additivity. But also don't forget, for phi we already have the sigma subadditivity. And indeed, this is what we should use here. Which means we get an inequality when we substitute the infinite sum with an infinite union inside phi. However, this infinite union already has a name, we called it A at the beginning. And in fact, with this last step, the inequality now looks very short. And we can make it even shorter by using the sigma subadditivity again. Which means this sum here now goes to a union inside phi. However, because we have A and the complement of A, just Q hat remains. And now, maybe surprisingly, on the right hand side we have the same thing as on the left hand side. Which means for all the inequalities here that we actually have equalities. In particular we get, because this whole equality holds no matter which subset Q hat we choose, the defining property for A being in A phi. Please recall, this was our goal all along, because it shows now that A phi is indeed a sigma algebra. In fact, we have also proven part B in the proposition, because this equality gives us the sigma additivity for our measure. You see this because Q hat can be any set. In particular, it could be A itself. And then we have measure of the infinite union is equal to the infinite sum. Okay, so here you see we have everything. This closes the proof. Now with this nice proven result, we are way closer to be able to prove the famous Carathéodory's extension theorem. And maybe we do this in the next video. Therefore, I hope I see you there and have a nice day. Bye!